So we'll get started. So I just want to know, like, how are you guys doing? I'll also open up my interface where I get to see, how we are all progressing. And usually, people who join this meeting are not, I mean, are the ones who are doing well. So I see Ankit has finished week one. That's great. And then there is also, okay, but that's it. My God. Who else? Oh, okay, they're at the bottom, I see. All right, a lot of us have finished actually, but some of them are carryovers from last batch. Okay, Aditya is from earlier, Adish has finished, great work. Cool. So we'll just do a quick round, like I want to hear from all of us. How is it going? Um, and so, Pratim, you want to start?
Yeah, going good actually. I think I completed week one and then week two also. I am now doing the assignment.
Yeah, fantastic. I see you're
So
at 97% in week two, so well done. And
yeah,
uh,
thanks.
yeah, so today what we're
So
gonna do is revise week two. So I think it's
yeah,
great that you've seen the videos. I think you're in the best position to kind of make use of the time.
yeah. One question I have is like the correlation between week one and week two, where we left in week one, the gradient descent actually, and
Mm-hmm.
in week two we started with a different kind of concept, forward prop and back prop. So how gradient descent is related to forward prop and back
Yes,
prop, all
we'll
those
come to that. So
interrelated
we
things
use the
we will
gradient to do
discuss.
the update, and the gradient comes from backprop. But we'll
Okay,
come to that. Yeah. So we'll
okay.
discuss
So
this. Yeah. I just want to like talk to everyone and see where we all are. Adish, how's it going with you?
Doing well, actually. I just revised week one, two, and three. It has been months since I actually last time it was in like April or March, right? So it has been
Mhm.
months. I had to just rewatch all the videos.
Cool. Awesome. Pranav, how are you doing?
Hello, audible?
Yes, you're audible.
Yes. So actually, I also again revised some concepts because I joined a couple of means last quarter, so I revised those. Also
Mm-hmm.
gone through week one assignment again. I have submitted already, so I gone through that. And right now I'm working on a second week's two assignment. So I almost done with that. So I will submit it in day or two.
Fantastic. How about you, Anish? I see you've already done week one. Week two also, you're like done all the videos, so that's amazing. You
Yeah,
want to share? Yeah.
so I have to start an assignment. I think a couple of like points I wanted to discuss actually would help is that this Jacobian and like gradient. I mean, I broadly understood that we are essentially like the uh, like whatever we get from the error, we are trying to propagate backwards.
We're gonna
But
discuss this, so I'm gonna
yeah,
talk all about it. So
yeah,
just give me
yeah,
a few minutes. Let's just
sure,
go,
sure, sure.
just go over
Yeah.
everyone, and then. So Sharath, hi. I see again, like, well done. So you're also 95% on week two. So only the assignment is pending. Anything you want to add?
No, I could only get the courses of week one. I joined the course late because of some medical emergency last week, and
I'm so sorry.
this week assignment was stuck because of a GitHub issue that I got resolved finally today with Harsh. So I will do
Okay.
the assignment and then continue on week two.
Wow, very inspiring. I mean, so that's great. Uh, then who else is here? To Sharath. Okay, then it's the TAs. Then Pranav. I think we already spoke. All right. No, no. Yeah, Pranav, how are we doing? Again, you're doing well. I think you're attempting the week two assignment.
Yes.
Cool.
Yes, I'm attempting second week two assignment, so it's almost done. But some things I'm means while concepts are clear, but in coding those assignments, I'm getting some NumPy related issues. Means some things I have not used earlier out of the box.
Yes.
So I'm learning those things as well. So it's
Yes.
bit kind of a tough assignment, not that simple, straightforward assignment. Means
The week
so
two is the most difficult, or one of the most difficult assignments in my opinion. So thanks for hanging in there. Yeah. Arnav, I see that you've also done. 60% of week 2 videos.
Yeah.
So good work. Satyamurthy also, I mean, you started week 2, you're 35% week 2 videos. That's also very good. So Ankit, okay. Ankit, how's it going? Again, week 2, 35%, right? So not bad.
Actually, stuck at backpropagation. Like I had to see that video a couple of times, and I
Okay,
understood
you'll see the video
about.
again once, like in 5 minutes. So
Yeah, yeah.
I'm gonna talk about the same thing, and we can stop. We can talk about like just interrupt me whenever it's a little bit confusing, right? Deepto, again, you're doing very well. Week 2 assignment. Very proud of you. Well done. And now, Akash. Okay, Akash Raj, how are you doing?
Hi, Arjun. I'm doing good.
Yeah, awesome. You're oh, okay. You're from the previous batch, right? So, okay, cool. And now, fast code folks. Danina, Jaiprakash, Pratibha.
Yeah, hi Arjun. Yeah,
Mm,
so last week I started the course actually. So it
mm.
seems nice, like how,
No, I don't want to know how it's nice. Like, so okay, you're at week. Okay, so you're also doing good. So good progress, right?
yeah,
So you're also, yeah, week 2, week 1 assignment. No, you're like week 1 assignment is pending, so you're behind.
yeah. So the GitHub issue like today I tried to solve, but I found the GitHub issue 404 issue. So I have to resolve that by today itself.
I mean, like like whoever who made all the assignments sits right next. So this is like if coming from you, it sounds like an excuse. Danina, very proud of you. You're doing very well. Second week you're doing 31%, so that's amazing. And you've done the week 1 assignment. That's the way to go. I mean, who else is here from Fast Code?
We have Kunal and Pratibha.
Okay, Kunal, how are you doing?
Yeah, I'm doing good and did the
Okay.
first week assignment, but I'm not able to see the second week's content yet.
Yeah, but like you have to ask Amina for that, and Amina's right here. So, like, just ask her, and she'll open up week 2 for you.
Oh, okay, yeah, cool.
Pratibha?
Yeah, I just joined in the last weekend, so I'm yet to start with the course like for week 0 and
But if you joined last weekend, why did you not do something in the weekend, like before the last weekend?
I'll do it right away.
Please,
Yeah,
right? Because again, you'll have to meet me every day at work.
yeah.
So,
We have Vivek also.
oh, okay. Hi, Vivek.
Hi Arjun. So I'm currently at week one's
Yeah.
assignment.
Okay. You're also lagging behind a little bit, so please catch up.
Yes, definitely.
Yeah, because okay, perfect. So we are 10 minutes into the class. Anyone else? I forgot. Okay, Mohan is here. Hi, Mohan. Nice to
Hi,
see you.
hi, yeah. So hope everyone is doing fine. So basically, I have completed week 8 assignment.
Mm-hmm.
Two weeks before I have completed. Yeah.
Yes.
So
Congrats.
only the capstone is pending.
Yes. So, yeah, because of that, I don't see a badge on your name. And what we also do is like after the course finishes, so Amina, you should send out the form like we always do for recommendations. And then based on how we have interacted, we ask you to fill a few forms. And whoever wants to kind of get a recommendation from the TAs, from me, we would be very happy to provide after the course is done successfully. So yeah, hang in there.
Okay.
Yeah. Cool. Denina, how did you manage this? How did you get a certificate without finishing the course? You hacked it. You told Vishal to generate one for you. So there's a bug here, Amina.
Yes, I noticed that. Yes.
Yeah, so maybe she got Vishal to do something. Yeah. Cool. All right. So what we're gonna do, anybody else I missed?
Hi Arjun, Pratik this side.
Hi, Pratik.
Yeah, I'm like a bit behind with the course, so I plan to. I'm in mid of week one, so I'll
Okay.
plan to complete by this weekend.
Fantastic. So yeah, you're exactly at 50% in week one. But
Mhm.
yes, next time try to catch up, because what happens is in the live session, you will not be able to make, full, let's say, use of
Yeah.
your time here. But yeah, I know you started slightly late, so no problem. Cool, amazing. So what I'm gonna do is we're gonna go through, so the questions that we started off with, like we spoke about gradient descent. We want to go down in this loss curve. Then suddenly, why are we talking about backprop, right? And that is a great question to ask. So also today I have my iPad, and in my iPad, what I can do is I can write. So just give me a second. Screen. But am I able to broadcast two screens? How does it work in Zoom? Do you see two screens? How do you see it? Are you
There
able
is
to like
a
switch?
minimized screen and there is one plain whiteboard.
Okay, but are you able to like switch between them? Are you able to make that prime?
Yeah, it's appearing in two tabs. Yeah, for me.
Perfect. Okay. So with everyone, it's fine. Can I leave it like this? Can I have both screens open? Anyone who's not able
Yeah,
to
fine
switch
with me.
between? Yeah, thank you. Anyone not able to switch between them? Anybody is able to see just one? You want to try, everyone?
It's just the white screen for me.
Yeah, can you like swipe left, right? Are you on a computer or a
I'm on my
device?
laptop, yeah. I am not able to swipe right.
No, we are not able to switch.
Arjun, there are tabs on the top, so I think people can click those tabs to switch between.
Yeah, let's see.
Maybe.
Where is the tab?
I think it's on the top. It says meeting, Arjun Jain screen, and
Okay. Let me open my Zoom. Not here, right? Okay. We have to show
Yes,
them.
on view options, there's an option called view options. If you click on it, there are two Arjun Jain written here. You can switch between which tab that you want. Just click on view options, and below there it says shared screens, and there are two Arjun Jains written there. Whichever you click on, you'd be able to open that screen.
If it doesn't work, no problem. I mean, I can just switch off one of my screens. Anybody still not able to? Feel free to say, like it's fine. I'm also not able to find what these guys are saying, but maybe because I'm sharing my screen.
So where it says you are viewing Arjun Jain's screen, right next to it, there is an option called view options. Once clicked on it, there is shared screens below. Yes. So that's where you switch the screens from.
Let's take a minute, and if you're not able to, let me know still. No problem if you're not able to.
So Deepto has messaged that he can switch between them.
Okay, fantastic. Anybody still cannot? Feel free
Pranav
to speak
also
up,
says he's able
It's
to
completely
switch.
fine. Sorry?
Yeah, able to
Pranav
see.
also says he's able to switch.
Yeah, but we have to take like whoever's not being able to, anybody not able to, like just speak up. It's completely fine. Otherwise, we'll assume all of us are, and then if you're not able to see, then it'll be a issue for the next 20 minutes.
Meena, where is the view option?
Yeah.
Just right on top where you're able to see people's names and videos. Right below that, it says you are viewing Arjun Jain's screen. So right next to it, there's an option called view options.
Yes, I could see.
So when you click on the view
Fantastic one.
options, it says shared screens.
Yeah.
Anyone else who didn't get it, like just feel free to speak up. I mean, it'll happen every class, right? So, like, I wanna have my iPad and write some things on it, especially when we're getting deeper into Jacobians, gradients, etc. Anyone still? Take your time, no problem. All of us have it? Yeah, fantastic. All right then. Yep. So last time we were discussing the laws, and we said, okay, we want to go down in this loss landscape. And we said, okay, let's take a simple case when there are only two learnable parameters, W1 and W2. And then what we're going to do is we want to, and then on here, the y-axis is f of x. F of x is the loss, right? The loss is a concept which we have looked at. It basically is the unhappiness of our output, how unhappy we are with our output. And what is the loss function of? The loss is a function of your input, your target, and your weights. Yeah. So you can only compute loss when you have a target, when you have ground truth. You can do a prediction, but you cannot compute a loss until you have ground truth. Yes. And what we want to do is we want to find the best values of W1 and W2 such that we get minimum loss. Such that we're able to minimize our unhappiness with the output. And how it relates to, so this is gradient descent, right? All we are doing is going down the this loss landscape, and this is gradient descent. But then why are we, like, what are we doing when we're doing this neural network? So we are trying to see how to use this gradient descent for neural networks. And when we do neural networks are usually, built of multiple layers, multiple modules. In this case, okay, there's some chat here. So, I mean, you're looking at the chat, right? If there's anything, you let me know. Yep. So this neural network, for example, here is made up of 5 layers. This is layer 1, this is layer 2, layer 3, layer 4, layer 5. Usually what happens is, and we'll talk about more later, so you have, let's say, a layer, a module with a weight. So you can think of this, let's say, as your simple linear layer that we did, right? So if you just do your W1x, this is just the linear layer, and this is, let's say, what is done by just your layer 1. Layer 1 is just doing this function. And then this is creating my activations 1. And then there is usually a non-linearity, and the non-linearity usually doesn't have any learnable parameters. We'll see sometimes they may have 1 or 2 learnable parameters, but usually they don't. And we need this non-linearity for, otherwise something bad happens. So we'll talk about what. And I want to ask some of you, first the students and then the TAs, why do we need this non-linearity? This is also like, a very typical interview question, a basic screening interview question that you would hear when you get into machine learning. And then you will again have, let's say, another layer. And so this gave us A1, and this A1, we would put it into another layer, right? So here, this nonlinearity is represented using the function G. And then this function G, so this function G would give us A2. And then this A2 would go into this another layer. So you can think of this as another, let's say, linear layer to start with. So A2, we would do another, let's say, W3 A2. And this would give us A3. So we get A3. And A3, again, we put it through another nonlinearity, J. And this then gives us what this J, then this gives us A4. And this A4, we apply another W5. And this gives us the final output. So this is the forward prop, as we call it. So these are terms. Vocabulary is very important because then one word would exactly, you would understand what exactly I'm talking about. So forward prop is the word that we need to remember when we are talking about the forward function. Now, students, before we go to the TAs, why do you think we need this nonlinearity? What happens if we don't have this nonlinearity?
Then it will become just one matrix, like it will be like
Exactly.
It will collapse into one linear layer actually.
Exactly, right? Because then what is happening is we don't have this, and then what we have is W1, W3, A2. And then why not write W1, W3 as just another, let's say, some W13. So everything then just becomes another linear layer, and this is why we need this non-linearity. So, I mean, later on, we also talk about when we talk about activation functions. I show this using a didactic example. And I think for those of you where it's not fully clear, we will get to it. Okay, let me wipe this thing clear. 1 second. Okay. So now we have this output. So your X goes to the layer 1, gives us the first activation, non-linearity, activation 2, another layer with learnable parameters, activation 3, non-linearity, activation 4, final output. The output along with the target, the ground truth Y, goes into the loss, right? Now, again, this is a simple interview question. What is the output of a loss function? Is it a scalar? Is it a vector?
Scalar.
It's always a scalar, right? That is how you define a loss. Because otherwise, it will become very difficult to compare two losses. Which is a better loss? 1, 3 or, 2, 2, right? So how do you know which vector is better? It's not possible. And this is why we need a scalar. Only then we can, go in the right direction. So loss is scalar, and we are able to compute our unhappiness with O based on this function. And now this is simple vector calculus, right? It sounds fancy and it looks so difficult, but it's nothing. It's just saying, okay, you just take one component and one component at a time and apply your simple 11th class, differentiation to that. And if you want to define it formally, and I would recommend you check this out. So your X belongs to R to the power n. What does it mean? It just means that your X is a vector of size n cross 1, y n cross 1. It could also be 1 cross n, but we have decided that our X will be column vector. This is, we have decided. Otherwise, everything flips. You can choose it to be a row vector as well, but then everything flips. Then your gradient becomes a column vector. Right? So, and what can it be filled of? It can be filled of real numbers, right? 0.5, 6.3. So this is how you define this space, this vector space. And now let there be a function. And what is this function doing? It is taking this vector and it's giving out a scalar. Why scalar? Because now we are going to this real number. So it will give me one single number, right? 0.6. Now what we want to do is we want to differentiate this with our vector x, right? So we want to differentiate essentially our loss with this vector x. And when we do that, we create this so-called gradient. Now gradient is a row vector. What is the size of this row vector? It is the same as the size of my input, which is n. And each component of this gradient is essentially, your derivative of f, which is this, but only based on our first component of x. What is the first component of x? This thing. So then everything else remains constant. And so this is your partial derivative, right? You consider everything else to be a constant. Any other term depending on this is a constant. So everything else usually becomes 0. Then it'll go on till dou f by dou xn, right? And when we are doing this, we are only differentiating it with the last component of my vector x. So this is the gradient. And we just use it, the math then checks out and we use it for optimization. So any question here? No, right? It's simple. And now we just take this a step further and we say, okay, we want to differentiate not just, we want to differentiate a vector with a vector, not just a scalar with a vector, right? So I have now a function which takes in a vector and it actually gives me another vector. This can be of a different size. This is why I've drawn this one to be smaller, this one to be larger. Yeah. And now we just play the same game. You say, okay, now because I want to, like now what you want to do is you want to differentiate your, so if f is taking your Rn to Rm, the derivative of then of, just this part with this part. So remember, though we have put f here, this is actually your f of x, right? Because we're just showing this here, and this is your x. So we differentiate this with this. Then we differentiate this with this. We differentiate, sorry, we differentiate this with this. We differentiate this with this. We differentiate the first one with this. We differentiate this with this. We differentiate this with this. And that is how we create the first row. Then in the second one, we differentiate this with this, differentiate this with this, differentiate this with this, and we get the second row, and so on. And this is what we call the Jacobian. And these are just two definitions that we want to use because we want to do this differentiation business, because we want to do this optimization, because we want to do gradient descent, because the quantity that we're interested in is dou L by dou W, right? Because we want to update W, because we want to find good values for W. Yeah. Any questions? No? Cool. So, like I said, these are the three things that we're interested in. We are not interested in any other gradient, right? Like we're not interested in any other quantity, but to get this, we need all of that. Because this is all we need. If somebody magically gave us this, if an oracle gave us this, we could just take it and update our weights and be happy, right? But we're not getting all of that. So suppose I want this quantity, the last quantity, right? Dou L by dou W5. How do I get it? What I want is dou L by dou W5. But what is L? We've defined it here. L is some function of O and Y. Y is usually a constant. O is, comes from here. But can I differentiate O with W5 directly? No, I cannot differentiate O with W5 directly because, like, so, I mean, you can differentiate O with W5. Why? Because O is a function of W5. Yes? Because how do we get O? Second.
It is a function of the last layer. I mean,
Yes.
being expressed is a function of last layer.
Yes. So your O, how are you getting O? O is some function. I forgot the name that we use for this. Let's just call it F for simplicity. And then what is it taking? It's taking A4 and it's taking W5. One example of this function W can be your linear layer, right? So if it was a linear layer, which is usually the case for neural networks towards the end, then what would it become? It'll be W5 into A4. Yes. So now your O is a function of W5. And what I want to do is I want to differentiate this. So what we are looking for is dou L by dou W5. And what we are able to get is dou L by dou O, right? We don't have directly this. So we can get this here. And the last layer is still easy. But if you want to do it step by step, what you want to do is you want to first compute dou L by dou O, because you can directly compute dou L by dou O because loss is directly a function of O. So dou L by dou O is very easy to compute. And now, what will be the size of dou L by dou O? It will always be the size of O, assuming the size of O is M. Then this will be a row vector of size 1 cross M. Yes. And now with this, we can compute dou L by dou W5, right? So now what we want to do is we want to differentiate dou O by dou W5. And here, this is directly a function of W5, right? So we can also directly compute this quantity. This is output is a vector, W is a vector, so we get a Jacobian. What is the size of this Jacobian? The size of this Jacobian is M into size of W, right? Let's just denote it like this. So m into size of w, and we will multiply this 1 cross m because it's a row vector from the left side. So what we will get is 1 cross m cross w. So our output vector will be of size 1 cross w, right? So this is the gradient which is of size w. And now with this, we can update our weights. So your W5 is a function of, these two partial derivatives that we computed. So the first one is a gradient, the second one is a Jacobian, and then when we multiply it, we get the gradient with which we can actually do this update that we are interested in. So with this, we can update. And like the last one is a little bit, let's say, easy, right? Because you could have also written your output as a function. Suppose we're doing linear, so we're just saying W5 into A4, and then you can differentiate this directly with W5. So, but then we still kind of wrote this as this, right? But now suppose you were to do it for W3. This becomes really difficult if you don't follow the chain rule. Yes, and now to some whoever, sorry, like I didn't see who asked the question, but why are we computing, why are we doing this backprop? The whole backprop business we are doing is to compute this gradient. Because once we have this gradient, we can do gradient descent on the parameters of W5. So, I mean, does that answer your question?
Yeah, yeah, and we have to do it with multiple W's, right? All the way
Yeah.
down to the layer one.
We have to do it with all W's. We have to do with all learnable parameters that we have in our network.
Okay.
Because we started with random values for those learnable parameters, and what we want to get to are good values so that we get a good output, we get a low loss, so we are less unhappy.
Oh.
Right?
Arjun,
Yeah.
quick thing. I think in front of you, you have two different screens, right? And you can see both of them simultaneously.
Yes.
For us, we have to at one point in time, at least I can see only the slide, and I have to manually go and switch to iPad. And it's difficult to follow because we don't at least I don't realize when you switch to iPad versus when you're on.
Understood.
I don't know if other
Understood.
people are facing the same issue, but I'm guessing it's the same for everyone else. But just wanted to
Got it.
clarify.
I agree.
Thank you so much,
No,
Sudesh.
The
you
PPT
can
screen is minimized. When the whiteboard is open, the PPT is minimized, but it's there on the screen.
Yeah,
But
Yeah,
when you
but
move to
PPT
I
is
think they
open,
cannot read it. Yeah. Got it.
and
So
when
Sudesh,
PPT is open,
point.
whiteboard is not there. Yeah.
Okay, point noted. So what I'll do is, let's then, okay, let me stop sharing here. And I want to do a
I have a
interesting.
solution. I have a solution. I am able to see both the screens simultaneously. You can pop out the tab and you can split the screen. You will see both together.
Oh, that's a great idea, Pratik. Thank you. Are you able to do that, Sudesh? Like pop it out?
Like, can you, what exactly do you mean, Pratik? When you say pop it
So
out?
you will be able to see, you are able to see two tabs on the top, just like the browser's tab, right? You can pop one of the tab out
What he means is
in
just
half
drag
of the
it,
screen.
maybe. Yeah, so then it'll become two
Mhm.
screens, like you do it on a Chrome tab.
No, there is an option which says pop out.
Okay, even better. So does that work for you guys? Sudesh, does it work?
Yeah, okay.
Yeah, it's fine then. You're able
Sorry,
to
but
see both of them?
where is that option? I didn't get that. How to pop it up? Pop tab.
The two tabs that you see, maybe right click on that or something. Pratik, right click or yeah, then it'll show pop out.
Yeah, there is a three dots on the tab.
Siddesh, were you able to find that pop out?
I'm actually also looking where exactly are the three dots. Do you mean the more option at the bottom of the screen?
No, at the top where you see the name of Arjun.
At least
we are on Windows. It might be different for like if you're on Mac.
You're on a Mac, maybe.
Yeah, I'm on Mac.
I don't think that works on Mac.
Got it. Okay, so then, okay, let's just look at this, my whiteboard for a minute. Yeah. Are you able to see this well, Siddesh? This is good, right?
Yeah, the one screen is fine. Yeah.
Yes, perfect. Works on the Mac as well, Adish is saying. Yeah, they cannot leave Mac people, so behind. Anyways, let's do this. So, have we? So I want to. So I mean, the example gets very clear when you do it manually for, let's say, the fully connected layer, right? Like the Jacobian business. So what we want to do is, this is your fully connected, and this is essentially your matrix multiplication in action, right? And suppose this is my input vector n, this is my output vector m. So then what would this, and let's call it m1, m2, m3, m4, and let's call it n1, n2, n3, and n4. And let's call this w11, w12, and so on. So who can tell me what is the value of m1 in terms of w11, w12, assuming our weight matrix is, w, and we have our inputs n1, n1 to n4. So this is a fully connected layer. So what is the value of m1?
N1 into W11
Mm-hmm.
plus N2 into W12 plus N3 into W13 plus N4 into W14.
Perfect. And similarly, for m4, it's gonna be n1 into w41 plus n2 into w42 plus n3 into w43 plus n4 into w44. Right? Here is w11, here is w44. And now we want to differentiate. So what we were saying is, if I want to compute, let's say, the Jacobian matrix, so what will my Jacobian matrix look like if I want to differentiate the output with respect to input? So dou m by dou n, what will it look like? What is the, so what will the first term be? It'll
Dou
be
M1
by
dou N1.
perfect. Next.
Dou M1 by dou M2.
Perfect. Dou m1 by dou n4. Similarly, it'll be m2, m4, right? m3, m4 in the numerator, and it'll go on from n1 to n4 always. So now let's just look at this term, right? Dou m1 by dou n1. So we want to differentiate this m1 by n1. So we want to differentiate this whole thing by n1, right? Sorry for the mess. So what will happen? What will be the, when we differentiate this whole thing with n1, what do we get?
You will get only W11. So it's
Yes.
kind of diagonal.
We get only w11. Why? Because nothing else is a function of n1. So we treat all of them as constants, and then they become 0. And then when we differentiate n1 w11 with respect to n1, you just get w11, because derivative of x is 1, right? When you do d by dx of x, it is 1. So you're doing d by, so you can take this is a constant, w11 is a constant in this case, right? So you can take it outside, and then you differentiate that. Oopsie, sorry, my bad. Oh, that is gone. But you got the idea, right? So we were essentially creating the Jacobian for you. And that was the whole Jacobian. And now we want to use that kind of a Jacobian and the gradient to then do our gradient descent. So now let me stop sharing this, or I mean, maybe let me share it, but you don't have to look at it, right? So now I'm gonna use my screen. So what I was trying to show, and you have videos for it, and like what I was trying to show is that, okay, we got the gradient here, but now we sometimes wanna. So now what we want to do here is, okay, we're done here, but we still need to back propagate so that we are able to get the gradients for W3. And to do that, what we have to do is we have to compute this Jacobian, right? So it is output. So we have the Jacobian of the output with respect to A4, right? And we what we do is we multiply this Jacobian with this. So this is very important, right? So usually we have two kinds of gradients. One is the gradient with respect to the weights that we use within the layer, and one is the gradient with respect to the input or output, however you want to call it, that we pass to the previous layer. So we have this Jacobian dou O by dou A4. We multiply it with this gradient dou L by dou O, and we get a gradient that we pass to the previous layer. But now this layer has nothing to do with the gradient, right? Because it has no learnable parameters. So then we have the only function that it has is it doesn't have the grad input method. It only has, you know, the other method. It doesn't have the grad weights method. It only has the grad input method. So all it needs to do is it needs to create the gradient so that it can pass it to the previous layer, so that the previous layer can then use that gradient, create its own Jacobian, and then create the gradient for its own weights, and then create another set of gradients that it passes to the previous layer. So anyways, we have this Jacobian. We got this gradient from the previous layer, right? So this much, the first two things are the gradients from the previous layer. This is the Jacobian of this layer. And then this gives us the gradient that this layer 4 passes on to layer 3. Yeah. And now we have, so now what we want to do is we want to use this gradient, right? So this part of it, this first three part of it creates its own Jacobian, this dou A3 by dou W3. And then using this Jacobian and the gradient that we got from the next layer, if you multiply, you see that you get the gradient that we are actually interested in, the gradient with which we will actually be able to update the weights. And that's it, right? So these are like generic things, and that's it. That's all that there is in backprop. And then we use like, so once we have the gradient, we can use gradient descent here. Once we have the gradient, we can use gradient descent here. Yeah. And yeah, then there are like, you know, general purpose things which we have, I don't know, I don't remember how much have we, okay, let me just see here. So how much do I cover in my videos is what I'm trying to see. Because I want to go till there in terms of the explanation today here. Anyone wants to help me? Like, how far do we go in week 2? Module 2. Okay, I just want to
So
see.
then we extend activation function, ReLU and everything.
All right, then we do it for each of those, right? And we then
Yeah.
kind of, yeah, okay. And that's it. Okay. Got it. Yeah. And probably we also talk about, yeah, the other thing. So then what we do is we then apply this and create this for these multiple activation functions. And why? Because this is then used in the exercise. And then what happens is when you actually do the exercise, when you actually do the assignment, you end up creating something that was like PyTorch. Like back in the day when Jan created his Lush, so this was before Torch. He did it in Lua, and it was just this because there was no GPU. And what you will create is what Jan LeCun created, maybe, you know, I don't know, in the 90s. So, but yeah, then there were other constraints, but this is what he exactly did by hand. And this is why it's important, because then you get a full feel of how the software engineering underneath this gradient descent and underneath this backprop actually works. So yeah, I know today was slightly long in terms of my monologue, but I thought it's important because this is where things get real. So yeah, I think rest of it, I think if you follow this much, rest of it you will be able to follow. And you know, I want to open it up to discussion. I want to open it up for questions. You wanna, you know, anybody wants to start?
So, Arjun, this is Sharat.
Yes, yeah, Sharat.
Frankly, from the linear classifier, the first 10 minutes when we shifted to gradient, it's like too fast for me. So if I, for the sake of simplicity, try to imagine what we did in the front and back propagation, going back to that 3D gradient. in the linear classifier.
Mm-hmm.
So what we are doing, and if we simplify further the bell curve, we see the gradient and we go opposite. Are we doing by back propagation? We are going to a different starting point.
No,
Once
sir.
we
You
learn,
almost had it. So with backprop, all we are doing is we are finding that loss function for different W's, right? So we're finding that gradient so that we know which direction to take the step. So we're just finding the gradient because we're not able to find the gradient directly with respect to loss. So we're essentially finding, the slope of dou L by dou W, and then we want to take a step in that direction. But we're just finding the slope with backprop, but then we use gradient descent. So, I'll again share my screen one second. Yeah, let's not go on here. Yeah. So, we'll just see this for a second, right? So we want this dou L by dou W5. We want this dou L by dou W3. And let's assume all these W's are simply just two parameters. Yeah, because so that we can visualize it. So now, let's say W1 is made of two parameters, W3 is made of two parameters, W5 is made of two parameters. So what we want to do is we want to find this gradient. But to find this gradient, we have to do the backprop because what we're interested in is this gradient, right? Dou loss of W by dou W1, dou loss of W by dou W2. But we're not able to get it directly because there is no way to differentiate L with W3 without doing the backprop, without applying the chain rule. Does that make any sense? Maybe one of the students, if you want to explain, like who has understood it recently, maybe that'll help. Siddesh, you want to try? I don't want to put you on the spot, but anyone else, I think you'll do a good job.
Yeah, sure. So I think, like, if I have to put it simply, so we take a random W, and basis that random W, we kind of try to create an output, right? Now that output was created basis a random W, and we need to kind of optimize the W such that we get the right output. So the optimization function essentially becomes a loss function, and now you kind of need to decrease the loss. Now decreasing the loss essentially means, like, if you find the right W, the loss will be minimum, right? The question is about how do we find the right W so that the loss is minimum. So we try to take little steps from the point that we have started so that we can move to find a W which gives us minimum loss, right? And the way to take those little steps is essentially gradient. That gradient, like, is in a way a step, and we keep on taking multiple steps to minimize the loss. And the backprop essentially helps us find the direction of where we should move in that multidimensional space. I hope that
Yeah,
makes sense.
absolutely. So essentially, yeah, like that backprop is essentially helping you find this because you cannot find this directly because you don't have this, because you don't have loss as a function of your weights. In this case, you do because it's a simple linear one. But otherwise, your loss is not a function of W directly. It is a function, but in a convoluted way, right? Because you have to apply the chain rule to get to this simple part. Does
so
that? Yeah.
the back propagation is just that loss as a function of weights, which is straightforward which is a gradient in that heat diagram. Otherwise, this is what it's doing. Okay.
And yeah, so like what we want is to get to that diagram, but we're not able to
Yeah.
get to that diagram because, for example, here W3 is not a function of like loss is not a function of W3. So what we want to get is dou L by dou W3, right? This is the gradient that we're interested in. If we have this, we are able to take this step, but we are not able to find this step until we do all this chain rule because you cannot do the math. You cannot directly compute dou L by dou W3 because loss is not a function of W3.
So go forward to get loss, and then go backward to do the do dual by do W.
Yeah, I mean, you don't really need the loss, you need the derivative of the loss. But yes, you
Derivative.
still need to go forward to compute the outputs because only then you'll be able to compute the gradients of these intermediate steps.
Yeah.
So yes, to do backward, you do need to do forward, and that's a very good point.
Yeah. Yeah. Otherwise, I understood the concept of gradient and how you move incrementally. Just the multiple layers, it was difficult to imagine. I think once I see this again, I'll probably get it better.
I think once you do the assignment, it'll become super clear because you have to actually code it up. So before trying to see it, try to do the assignment. And then reach out to us on Circle, others will also benefit if you do. Or WhatsApp or what. Thanks, Sharad. So thanks for that question. Appreciate.
And Arjun, one more question.
Yes,
In
Patan.
that gradient descent picture, you showed it as a 3D picture, and you showed two weights, right? W1 and W2. But for all practical purposes, it will be multi-layer kind of network. So it will be W1, W2, W3, W4, W5. So it will not be a 3D picture, right? 3D
Yeah,
plot.
never. Yeah,
It will
absolutely.
be a multi-dimensional kind of picture, and from there we have to find out the all the W values, which will give the minimum value of loss.
Exactly. You will never know if you've actually found the minimum, like the best values of W. But sorry, just give me a minute. Okay, sorry about that. Yes, so you'll never know if you found the right values of W, but you'll never know you found the best values of W. So whatever is the best value of W, you kind of say that, okay, this is something that I'm happy with, and you move forward with that.
Yeah, one more question. So basically,
Yes,
in the slide you mentioned that the new updated weights would be old weights minus gradient times the learning rate. So what is the numerical value, or what is the learning rate? How do we derive that learning rate?
That's a great question. Thanks for asking. So, learning rate is a so-called hyperparameter. Hyperparameters, whenever I hear the word hyperparameter, in my mind, I think a knob, right? So think of like a DJ console. There are these so many knobs, and you need to turn these knobs to find like the best music. So this learning rate is a knob. And remember, when we were doing cross validation, we said that we shouldn't overfit our hyperparameters on the test set, meaning you use the test set to find the values of your hyperparameter, or you do k-fold cross validation. You use one of the folds from your, let's say, training data to find good values of lambda. And we will again do this in the next, I think next week or the week after. But anyways, the way to do it is, okay, you use a large enough, let's say W, it doesn't work. You use a smaller one, you do kind of a random search in the space, and then you see, okay, what is the best lambda for which I get the minimum loss on, say, on my data. And that is how you choose the best value of lambda. So there is no science to it. There is no like mathematical way of finding that value. When you use a code base, you see, okay, what values did they start with? It's usually around, let's say, 10 to power minus 3. So 0.001.
Okay.
I know it's not very satisfying, but that's what we do, and that's how it works. Like there's no direct way to find the best value of lambda.
It's more like an iterative process, like a
Yes.
heuristic sort of a thing.
Yes. In real life, what happens is, like you turn it too low, it doesn't work. You turn it too high, your loss explodes. Then you find some middle part where it works decently.
Okay.
Yeah. Thanks, Ankit.
I have a question. Actually,
Yeah, Dish.
I don't want you to answer the question. I just want to understand which topic I need to be studying so that I can actually understand it. So I understand that dot product is like a projection. I can visualize that in 2D. Matrix multiplication is like a function, a transformation. I understand that. But when it comes now, let us consider a function fx equals to x square. Now, if we are differentiating it, it becomes f dash x equals to 2x or gx equals to 2x. Now it is again a function, right? A function. But when it comes to these functions which we are talking about, which take vector as input, and then we get a Jacobian. So Jacobian is a matrix, and then it looks like it is a transformation, and then it contains function in itself. So it looks like a function of function. So maybe I am somewhere I am.
No, you're complicating it. It's actually very simple. Don't think of a Jacobian as the full matrix. Think of it in terms of its components. So what you want to know is, okay, what is the slope of, let's say, kth component of input with respect to the mth component of the output? Rather, the mth component of the output with respect to the kth component. Like how much will the output wiggle when I wiggle the input? And just think of it for those components, like the components of the vectors, and it's like a permutation of all the components with each other. How much will the output change when I wiggle this? How much will the output change when I like the first component, second component, third component, and so on. So just look at each term of the Jacobian instead of the matrix itself.
But the output is just a scalar, right? But the gradient is, let's stick to gradient, not for the not Jacobian form. The output is just a scalar, and gradient is
a vector.
Yeah.
So, yeah, but think of your vector to be made up of, let's say, 5 variables, right? And now these 5 variables, think of each variable separately. So then for the first variable, it's still the slope. For the second variable, it's still the slope. It's just that you've collected all of them into this row vector called the gradient.
Okay.
But anybody else has a better answer? Anybody else wants to add to his question? If anybody else has thought of it differently, what Adish is trying to think? Yes, Sharat, like there is no local and global minima, and it's a moot point. Completely agree for multilayer. You can just think of all of them as local minimas. There is no global minimum.
Okay, so I will just give a thought about it, and maybe yes, I am complicating it.
Yeah, I mean, maybe you wanna like give a thought about it next week. Maybe you also get some time to think about it, yeah, because we don't have too much time remaining, and also like post it in circle so that we can also read about it before you present it next week, so that we can also come prepared, or I can come prepared, so that I try and understand what you're trying to say already. And sometimes writing it will also give it will make it linear. Our thoughts are not linear, but when you write it, you have to, it's a sequence of words, so you have to linearize your thoughts, and that sometimes helps, at least me, in in getting clarity.
Understood.
Anyone else?
Hi, I have a few questions from week one. So the first one is I could not completely grasp why we need the concept of bias in a linear classifier. Like I got that it allows us to like escape passing through the origin in the result, but I didn't understand that if we need zero as an output in our results in the resultant matrix. So how would that work? Yeah.
So these things, I mean, so Dipin is your TA, right? So Dipin knows this answer. I know that. And this week, you have your TA session coming up, or it
Yeah.
was? Yeah. So Thursday 6 p.m. you have it, right? So ask Dipin, and if he's not able to answer, I know he will be able to answer. But if not, we will again take it up next week.
Sure.
Yeah. Thanks. Anyone else? No? All right. So, I mean, for those of you like Sharat and others who had spent time on the videos, I think it's more meaningful. And then next week, what we're going to do is we're going to look at week 3. So your goal this week is to finish week 2, the assignment of week 2, and the videos of week 3. So videos of week 3 is something that you should do before our next session on Tuesday. And Yeah, like engage on Circle if you have issues, attend your TA sessions, and submit your assignments. So most of us are doing very well. So we should like congratulate ourselves. We should be really proud of what we have achieved because it's not easy. Like given everything else that we're doing, I know like how difficult it can be. So keep at it. Ask for help. We are here. We will, go above and beyond. We'll do special sessions for you, whatever it takes for you to be successful. Reach out to Amina, but please finish these. So I know it's like really intensive and we maybe don't have enough time, but let's see what we can get to. Yeah. So all the best and see you next week.